So it's 2019, and we're all very much aware of the fact that climate change is a serious issue. Now, if I were to ask everyone in this room to tell me what we should do to be more sustainable, we'd come up with the first things such as using less fossil fuels, flying less, maybe driving an electric car, maybe changing our diets, bringing our bags to the supermarket, using less plastic, and recycling. And all of those are valid and good. But there is one sector we almost always overlook. And this sector, in 2017, accounted for almost 40% of the global greenhouse gas emissions. Can anyone think of what this is? It's the building and construction industry. And this is not going to get any better in the future, because by 2050, there will be 2.1 billion people more on the planet. So whether we like it or not, we're going to have to build housing and infrastructure for them. And if we do things the way we do today, we're going to be faced with more pollution, resource depletion, and a whole lot of waste. So at the Block Research Group at ETH Zurich, we develop methods to build and design buildings better. By intelligently including structural performance in architectural geometry, we can really reduce the amount of material that you need for a structure. And I can explain that easily using this piece of paper that I carried in here. So when it's flat, it can barely hold its own weight. But if we change the geometry and introduce a little bit of curvature, it can suddenly hold a lot more. And the amount of material has definitely not changed. Now, it's the same principle that allows that Pringle to hold a full glass of water, and please try this at home. Also, it's the same principle that allows for this structure behind me to span 40 meters with only 6 centimeters of concrete. So if we do use structural geometry intelligently, we can design beautiful structures that use very little material. But there's a catch. Their geometries are usually complex and intricate, non-repetitive, and that means they can be very challenging to build using traditional techniques. Now, concrete is the most used material, not only here in Bucharest, but the world. So it's also a favorite material when it comes to these kind of geometries. Simply put, because it's liquid stone, so we can mold it into whatever shape we want if we have a formwork. And the formwork is the catch. If we look at how things are being built today, unfortunately, we find a system that has remained unchanged for hundreds of years. This is roughly the 1960s, and while we've gotten better and more precise and more streamlined in our manufacturing process, the basic principle stays the same. We need months of milling or carpentry to produce these heavy, clunky molds that need a lot of support and ultimately turn into a pile of waste. So really, if we want to unlock the full potential of these kind of efficient and optimized structures, what we really need to do is not only change the way that we design things, but we also have to change the way that we build things. In terms of formwork, one solution of many would be to use a textile. A textile is a lot lighter than wood, it needs a lot less support, and finally, it's also more sustainable. It produces a lot less waste. My research specifically looks at how we could use knitted textiles as formwork for concrete. And knitting is very special in the sense that we can create 3D geometries directly in a single process using existing machinery. And we can also make sure that we have very precise local material properties or integrated features. And if it sounds confusing, I'll have you think of your shoes. Your sports shoes all do all of these things, and you're very familiar with them. So how this works is we start off with a design and then produce a fitting knitted textile. We then tension that textile into shape. And because textiles, and especially knitted textiles, are actually quite soft, so you wouldn't be able to hold their shapes when casting, we just coat them with a very thin, special cement paste to make them strong enough. This leads us to a nice, lightweight structure that can be now used as a formwork for concrete. One of the tricky parts here was designing or coming up with a computational pipeline that allows us to automatically translate a 3D design into manufacturing possibilities for a knitting machine, for existing machinery. So let me show you some examples. Of course, just because we start off and we say, hey, you know, knitting could work, that doesn't mean everybody believes it. So I started off with this knitting machine, which is something that people in the 90s may have had in their homes, and we lovingly called her grandma. Of course, because she's the ancestor. So we did a bridge. The first bridge we did was a small structure, something about as big as the circle I'm standing on today. But it was important to be able to test this kind of principle. It weighed only 200 kilos, but the interesting part about it was how much the formwork weighed, which was about 1 kilo in itself. So the way this worked, or the way we tried out, was we started with a textile that we tensioned using some splines and ribbons into a corrugated shape. We coated it with the cement paste I mentioned earlier, and then we used it to cast concrete into normally. If we look at the textile itself, you'll notice that it has already some channels in which we could introduce these bars, these black GFRP rods, and cables to get to the shape. And we also had some registry points so that we would know that we get the right thickness of concrete. To produce it, we used grandma. It took about a week in this very automated and not manual process. As you can see, robots were not yet coming for our jobs. To produce this very small textile in 3 pieces, because the width of the machine was also limited. Now, what is very interesting about it is that it is very light. So the textile itself was only 433 grams in total. We put all of the pieces together into one single piece, introduced all of the splines and shaping elements so that we could get a corrugated shape in the end. That flattened piece of textile was then fixed into a rig, tensioned, and got into this shape. We took this lovely little bridge into a climate chamber and applied this thin cement paste coating I was telling you about to get a shape that looks something like this and weighs only 12 kilos. Now, this was 1 millimeter thick, and it could just support another 4 millimeters of concrete that we sprayed onto it. Those 4 millimeters, together with the formwork from before, became the formwork for casting concrete normally. So we didn't change anything about how we cast the concrete inside. The structure that came out may be small, but what it said about this kind of technique was that we can really create a rather heavy structure with a significantly lighter mold. Also, we didn't need support from underneath, so you could use such a technique to be able to build in places where you want to have an unobstructed passage, say over a highway or over a river. And of course, because we're researchers, what we also needed to do, we were eager to load test it dynamically and in a very scientific way, so we jumped on it. Now, to the right, to my left in the picture, is Lex. And Lex is the researcher that works on making sure that the composition of the cement paste is exactly right, so that it is strong enough to do these kind of things. So he's our in-house concrete magician. What the project also showed us is that the textile could possibly be used also in other ways. I mean, it wasn't coated on one side, so it remained visible, and we leave it in place, so it kind of brings an avenue of doing something architecturally and aesthetically with something that is previously just meant for structure. Now, those experiments were done with grandma, and you might say, hey, yeah, that's a great idea, but in construction, we need to do things that are a lot bigger, and spending a week on this 2-meter thing is also not exactly ideal. So we left grandma aside because those experiments were convincing enough to get an upgrade to a proper industrial machine, to see that this actually works at an architectural scale. So last year in October, we built a structure to test these things out. It was called Nitcandela, and it was built in Mexico City. It was done in collaboration with Zaha Hadid's Code Group, and it is designed as a homage to the famous shell builder Felix Candela. It looked something like this, and what you already see is that it has a concrete outside and something interesting on the inside, which is a textile. It weighed 5 tons of concrete in total, so we went a long way from the 200 kilos, and it was built using a cable net as a main load-bearing structure and a knitted textile that weighed only 25 kilos. In total, the cable net and the textile were 55 kilos, and they carried 5 tons. So that's quite impressive. To do this, what we did was we made a frame, we tensioned the textile into the frame using those cables that I talked about. But the interesting part here, just as with the bridge, is that the textile itself had all of the channels to guide those cables where they needed to be guided. And another nifty feature, it had pockets so that we could insert inflatables. When inflated, those pockets would create cavities in the concrete, saving weight. What we then did is we coated it with a very thin cement paste with a slightly different formulation because we needed to use it outside. And when that hardened, we coated it with concrete. When the concrete hardened, the frame can be removed and reused for other things. And we're left with a structure. As before, the textile is left inside of the structure, and it's what you see on the inside. It's this beautiful aesthetic thing. So in conclusion, the textile that we used had two sides: a beautiful aesthetic exterior that needed to be seen, and a technical other side that needed to fulfill all the functions of guiding the cables and where all of these inflatables needed to be, and for us to register the geometry. Even though they are two very different sides, they use two different materials and they behave very differently, they are produced on the machine in one single process. Now, of course, the machine also has a limitation in its width. It's not long enough. So we did have to split the 4-meter geometry into 4 parts. But when we were done, we created what is arguably the world's largest scarf, and we packed that up in 4 pieces and put it in our suitcases and took it in checked-in luggage to Mexico. Well, this is first to show that we can do this very lightly, but also as architects, we finish everything the night before the deadline. So when we get to Mexico, we put everything together, we introduced all the cables where they needed to be, and we stretched it in the frame. We also were very relieved to see that it does stretch to the size that we wanted, because it looked incredibly small beforehand, and that means that our pipeline and our whole system does work, at least until this point so far. And what you can also notice is how little support it has. Otherwise, you would need a whole lot of support to create this geometry. We then coated it with that thin cement paste layer, which was now misted on as a spray, and we were left with this beautiful Swiss chocolate of a texture on one side. Now, I just wanted to remind you that those little boxes that you see there of the Swiss chocolate, they're actually cavities in the concrete later on, making sure that we don't have as much weight otherwise in the structure. We then had very artful craftsmen, which are concrete workers in Mexico, that put 3 layers of concrete onto this surface in the most traditional fashion and made sure that it had an incredibly, incredibly smooth finish, which is absolutely mind-blowing to see that you get a concrete finish that probably Felix Candela would have also been proud of. So the finished structure has a hard concrete outside and a soft textile inside. What you don't see on this picture is that the textile is actually soft. You could lean against it, push, and it's soft because there are cavities behind it. And depending on how the sun would shine, every now and then you could also get a glimpse of the skeletons of little balloons that were in there. So I just wanted to leave you with a few thoughts about a process or a structure like this. The formwork for this was 50 square meters, and the cable net and textile, so excluding that frame that can be reused, only cost 2,200 euros. It was 25 kilos of weight that the textile had, and we took it there in a checked luggage. It took a mere 36 hours to knit a surface area that would have taken about 750 hours to mill otherwise. And the entire project, from the very first time we sat at a table for design to the structure standing there, was 3.5 months. That would have been impossible with traditional techniques, because those 750 hours I mentioned earlier, that's about 3 months of milling alone. So that would have been just the formwork. Now finally, the really interesting part is that those machines that I'm talking about, there are hundreds of them in factories such as these all over the world. So really, we don't actually have to take the textile anywhere, though it's light and all that. We can just send them the data and have them manufactured locally. Moreover, these types of feats of economy and productivity are incredibly important for the construction sector that is lagging behind other industries, and the productivity is at the moment the same as it was 20 years ago, lagging behind average and definitely a lot lower than what manufacturing can do. So considering that in the next 30 years, we would have to build the entire amount of construction that we have today. Bill Gates earlier this year likened that to adding a New York every month for the next 30 years. It's not that we can build less, but we should definitely be smarter about how we build and design those buildings. Thank you.